Yesterday, we talked about what happens when you drop two balls from the same height that only differ in how heavy they are. This ball is lighter than this ball, so we'll call them the light and heavy balls. When I drop them, we talked about the fact that they should hit the ground at the same time, as long as no other forces are affecting them besides gravity. But it's weird that that happens, because you should know that the lighter ball has a much lower gravitational force than the heavy ball does. So it probably seems to you like the heavy ball should hit first because it's being pulled more. But in actuality, something is affecting both of these balls that's preventing that from happening. And that something isn't a force, but it's kind of sometimes helpful to think of it as a force. And that something is the resistance that these things have to being moved in the first place. We call it inertia, and we talked a little bit about it yesterday when we talked about Newton's three laws. Newton's first law of inertia says that objects in motion stay in motion unless we stop them, and objects that are stopped stay stopped unless we start them. The amount of inertia something has is related to its mass. So the heavier ball has more mass, so it has more inertia. So not only is it being pulled harder by gravity, it's also harder to pull. This means that the two balls will wind up traveling side by side their entire trip. It doesn't matter how high up you drop them from. In every second of falling, if you were to take a snapshot of a picture of them as they fell, every second that they fell, you'd find that the whole time they were always side by side. And that's because even though the gravitational force is greater on the heavier ball, the amount of inertia on the heavy ball is also greater. And so the two things balance out. The rate at which things fall to the ground is the same for any object near the surface of the earth. Every single object, no matter how heavy it is always going to follow the same pattern. I'm going to draw that pattern as a series of dots that I call a ticker tape diagram. I'm going to show it to you for both the heavy and light balls. So the heavy ball starts there, and a second later, it's here. A second after that, it's here. A second after that, it's here, and a second after that, it's kind of almost off the page. The same thing happens with the light ball. Again, like I said, if we were to take a picture of them side by side the whole trip down, they would always match up perfectly. Why are the dots getting further apart though? They're getting further apart because both the heavy and the light ball are accelerating downwards. They're being pulled downwards by gravity, so a force is constantly acting on them, so they're going faster and faster and faster. In the first second that they're falling, they're going to pick up about roughly 10 meters per second of speed. So here at the top, they're going 0 meters per second. A second later, they're actually going to be going 9.8 meters per second. So they went from 0 to 9.8 in 1 second's time. In the next second, that 9.8 is going to double to 19.6 meters per second. And if we were to look at a little speedometer when we get to this point here, they're going to be going 3 times as fast as they were originally. So they're going to be going 29.4 meters per second. And then way down here at the bottom, about when they hit the ground, they're going to be going close to 40 meters per second. So if I add 10, so 39.2 meters per second. So they're picking up speed the whole way. This acceleration has a name because every object that we drop near Earth always accelerates the same way at the same rate. We call this the acceleration due to gravity. And the acceleration due to gravity is 9.8 meters per second per second. 9.8 meters per second per second. Every second we're traveling, we pick up an extra 9.8 meters per second of speed. We abbreviate this as G for gravity. G is going to be really important in the lab that we're about to do. That's why I bring it up here. The lab we're about to do is about energy. So here's the definition way at the top of the page in purple. Energy is the ability to cause a change. Anytime something is changed, it moves or its shape changes in any way, energy is involved. This lab is going to include 3 types of energy, even though there's really only 2 on this chart. Kinetic energy, over here, and potential energy over here. Kinetic energy is the energy of a moving something or other. Something's moving, you've got kinetic energy. The word kinetic is actually Greek for motion. However, objects that aren't moving also can contain energy, but they can be storing it for use later. So potential energy and kinetic energy can be changed back and forth between each other. The two that we're going to look at today in our lab are mechanical energy, which is the motion of an actual object. In this case, it's going to be your cart. And gravitational energy, which is a type of energy where you can store up the amount of energy in something by raising it above the ground. The higher up you make your cart go, the more energy you're going to be storing in it, and therefore the more change you'll get on the way down. Imagine that if I put something at the bottom that's soft and can be smushed by my cart that's coming down a ramp. You can imagine that the higher up on the ramp the cart starts from, the more smushed that substance is going to be when the car hits the bottom. And that's because our ability to cause a change is going up, 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 up as we raise the car higher and higher above the ground. All these other forms of energy we'll come back and talk about later, but for the lab, you really just need these two. Mechanical energy is the motion that you see of your cart. Gravitational energy is the stored up energy that you're saving up when you move the cart up the ramp. In the lab, you're going to be calculating the amount of energy that you get, and we're going to use units for energy called joules. These are like the word Newton. We invented the word Newton was a unit of force that we got because the units for force would otherwise be very, very ugly. They would have been kilogram meters per second squared, which is an ugly, ugly thing to write. So it's much easier to come up with a new name for a unit when that happens. So energy units are going to be joules, and we'll use a capital J to represent the amount of energy in something. And we're going to calculate the two types of energy that we get as PE for potential energy and KE for kinetic energy. Potential energy in this case is going to be energy stored up due to gravity. So if I take these two balls, for example, one's 2 kilograms, the other is 5 kilograms, and I've got them on a table that's amazingly tall. It's 10 meters tall, according to this over here. How would I figure out how much energy is stored up in those balls? Well, this is what we would do. We would use the formula. The mass of the ball, each one we have to do separately, times that constant we talked about, the acceleration due to gravity, g. That's 9.8, remember? Times the height above the ground in meters. So if we multiply those three things together, we will get a number, and the units are going to be super ugly because we're going to have multiplied together for mass, kilograms, For g, these are units of acceleration. That's the meter per second squared. And height is meters, again. So when you multiply all these things together, you get a kilogram meter squared per second squared. And that is so fugly, nobody wants to say that. So we call that a joule. Kinetic energy, instead of using G, we're going to use how fast the object's going. So we're going to take half the mass of our objects and multiply that times our velocity squared. And we have motion detectors that'll tell us what our velocity is. So we can plug all these numbers in and get our kinetic energy. And the same thing's going to happen here. We're going to get kilograms meters squared per second squared for our units, because the units for mass are for mass are kilograms. Our units for velocity are meters per second, and then we're squaring all of this, so we wind up with a kilogram meter squared per second squared, which is, as I said before, why we came up with the word joules. So as we calculate these things, what you're going to find is that because they both have mass in the equation, mass is important when you're talking about energy. The more mass something has, the more energy it has, both kinetic and potential. So even though the two balls are at the same height above the ground and will hit the ground at the same time if released, right, they won't hit with the same amount of energy. The one with 5 kilograms of mass is going to have a greater change impact on the floor than the 2 kilogram balls are going to have. So using those formulas is a big part of the lab. The third thing that the lab talks about is something called DE, and D stands for dissipate. Dissipated energy is the energy that you seem to lose as one form of energy becomes another. When you drop these balls, at first they have just potential energy. That potential energy gets converted into kinetic energy. In theory, you should have equal amounts of potential and kinetic energy. You should get the same amount of energy out as you had stored up. But some of it gets lost along the way. And part of what I want you to wonder about as you're doing this lab is, where's the energy that's lost going? Okay, read the lab sheets. Make sure you know exactly what you're doing. Make sure you ask questions if you need to. It's pretty much the same lab as the velocity lab with a slight change and some formulas thrown in just to, worry you a little, because I know you're all very nervous about doing math. But don't worry, it's very easy math, I promise, and I will help you with it if you need help. See you guys in class.